everything is working. So last time we were speaking about flexible and inflexible sort. And we said that you can make sort program to be flexible using permutation, which is, of course, far from the best way to sort things, but it can support flexibility. Flexibility is not supported by the library function sort. Sort is simply sorting input values and creating results and nothing else. In the case of the flexible sort, we can simply make a test program that checks whether a list is sorted. So list is sorted if it has one single element. This is anonymous element, and whatever element you have, list is sorted. Now, if you have more than one element, then you have head of list, and then second element A, and then the sublist B. So this is sorted if this head is less than or equal to A. So this is small value. And then from second element to the end is sorted. So you can say it is sorted if it has single element, or if head is less than second element, and from second element to the end is sorted. So you always have in PROLOG that you can never reach the second line unless you failed the first line. So you have always to go top down. And when we go top down, when we do that, then we have checking of list that is shorter than the original list. So original list has all its elements, and this list here has one element less. Obviously, that when we repeat this recursively multiple times, going through this loop, what is going to happen? Sooner or later, you're going to have a list that has a single element. Well, that is the boundary condition. And we put that at the very beginning, and this boundary condition is used to terminate the program. So if I want to sort a list to get the sorted list, so what am I going to do? I'm going to create a permutation of this list, which is this S list, permuted list. And then if the list is sorted, then we are going to return that list, and this is the result. If the list is not sorted, then we have to continue and do other permutations as long as we need to find the appropriate permutation. So if you have the list 4321, the sorted list will be S equals 1, 2, 3, 4. So this works and sorts the list. On the other hand, if you have that this sorted sort program is used flexibly, you can say, okay, I want to get the list 1, 2, 3, sorted list. What is going to be the input list? Well, input list can be 1, 2, 3, 2, 1, 3, 3, 2, 1. 6 of them. There are n factorial of them. And of course, this app sort program is trivial and it is flexible. However, unfortunately, it is factorial complexity. So nobody will sort in this way. But this is a toy program that shows flexibility as something that is supported in PROLOG. And you can have that either this first argument list is input, or the second is input. And you can have these permutations and compute S list from list or list from S list. And this is flexibility as one of fundamental features of PROLOG that we like to have in all cases. Now, how to deal with atoms that are not numeric? So if you want to solve, if you want to sort A, B, C, D, or Coke, wine, beer, and similar things, you have to teach PROLOG what is less than or equal to. So you have to say A is less than B. So this is the fact. B is less than C, simply because these are not ASCII characters. These are not strings. These are simply the symbolic values, so symbolic atoms. Therefore, we have to tell that A is less than B, B is less than C, C is less than D, D is less than E, for example. And then A, B, B, C, C, D, D, E, E are also less than or equal to, they're equal to. So now I want to sort A, B, C and get sorted list A, B, C. So here is the same program that sorts a single element by saying it is sorted, and then exactly the same program that we had before, except that now we have less than or equal to here. So we try to find this solution. And of course, if we say, can you sort this CBA to get this S, it gives me A, B, C, D, and that works fine. Also, you can say, I want to get list A, B, C. What is L? If sorted list is ABC, and you have all 6 permutations. Beautiful. But when you come here and say, sort me E, B, A, okay, to get A, B, E, you don't get sorted result, but says, no, that is not possible. Why is it not possible? Because there is no transitivity here in these relations. So you say that A is less than B, and B is less than C, and C is less than D, and D is less than E. But this does not mean that PROLOG understands that A is less than E. You have to make a particular program that is checking transitivity. So you have to have additional rules that you add if you want to have this to work. So these rules can be given here to have more such rules, or you can have transitive less than or equal to, so that it is less than that if it is less than or equal, or it is less than temporary, and then it is transitive from temporary to the final one. So if you have this transitivity, then you can do the same thing in this way. Another thing that we have here that we are going to skip is bubble sort and select sort. These are just programs that have quadratic inefficient sorts. Both of them work. You can check them if you want, but we are not going to waste our time studying this. If you want as an exercise to see how to append things that are sorted and what is the idea behind that, you can do that. I will go to do something else, to show you loops and repetitions. That means some procedural elements that we have in PROLOG. The first thing that we'll make here is this program that is making a list of natural numbers, so numbers from 1 through n. This is an example of making a library function. So in all problems that we solve on exam, you can have either that you can use library function, or you have to make your own function. So if the question is make your own function, then you must not use the library function that is doing the same thing. So you have to show that you can make a library function. So we did our own append function that is appending list 1 and list 2 to make list 3. So let us see how to create the list of numbers 1 through n. Obviously, that's if you have any number of numbers, you can make this list by having list that is going from 1 through n minus 1, and then append n at the end of that list. So to make a list that has 10 elements, you make the list that has 9 elements and then append 10 at the end. So the idea is very simple. If you have list of n elements, it is going to be empty if n is less than or equal to 0. So if you say, I want the list that has 0 elements, then you are going to return list that is empty. So this is the boundary condition that we have here. And then if list is not empty, that means if we have that number of elements is not 0 or negative, then we come here and we know that this n is positive. So to check that n is positive, once again, compute n1 is n minus 1. And then after that, make list that has n minus 1 elements. So make list that has n minus 1 elements and call this list 1. Then, when you have this list that is done, append to this list this value n. Please pay attention that appends lists. Lists must be a list. So you cannot say append L1 and n, because this would be a big mistake. You cannot take scalar value. But if you take list that has 1 element, that's perfectly legitimate. Append that to L1 and get list L. So you are going to go and append 1 by 1 values, 1, 2, 3, 4, 5, 6, up to n. Now, when you look at this make list here, this is recursive call of the first component. So when PROLOG comes to the first rule, it is trying to satisfy the first rule and return result. It is not possible because n is 10. Therefore, it is dropping down to the next line. So whenever you come here, for example, with this n is 10, you are going to now ask make list of 9 components. And this is going to bring you again to the first line. So it is making loop, first line, second line, first line, second line, first line, second line. In each of these iterations, you have n1 that is reduced by 1. So if this n is 10, then it is going to come here with 9, 8, 7, 6, and up to 0. And then when you reach 0, this is the boundary condition. And here you give the result. So it is going to have call, pushing all that in the stack. And then it is going to return by making these lists one by one. And therefore, appending these components one by one. So this is how this recursive sequence of calls works. And many problems are solved in this way. And this is typical tail recursive approach. So whenever you have lists, you decompose this list into 2 sub-problems. It is either by chopping head and doing everything with the rest with the tail, or by saying, I will solve problem of size n by first solving problem of size n minus 1. And then when you add the next one, you have the process that is creating all these solutions one after the other. Now, PROLOG has 2 control mechanisms that can be used for making loops. One of them is calling fail, this one here. So what is fail? Fail is the library function. Library function fail is telling the search engine, you just failed, and go and backtrack. That means this is a command that tells search engine, you have to go back and try to find another solution because this failed. And this unconditionally fails. And so when I have a program that has various lines, if I have here fail, fail is going to force me to go back. Now, there is another thing that is here used, and this is repeat. Repeat always succeeds. So repeat says you just succeeded with satisfying a goal, go and satisfy next goal. And this fail tells you just failed, go back. So this repeat and fail are like two tennis rackets. And search engine is like a tennis ball going between repeat to fail and from fail to repeat to fail, fail to repeat. So it is practically looping. And this fail is essentially go to the beginning, unconditional jump in this case, where inside you have only passive statements. So you have nothing that creates solutions. It is just something that gives passive results. So we have here repeat, and then after that put new line and write a simple prompt to the user. So what we want to do is we want to tell user enter an integer or stop to end the program. So the user comes and enters 3. And then you compute square root of 3. Square of 3 is 9. And simply say square of 3 is 9. And this is the result. And after that, we want to repeat that over and over again. Enter integer or stop to end the program. You enter 32. After 32, PROLOG program will compute square of 32 is 1024. But if you have this prompt and you enter the symbolic constant stop, which is the atom, just not numerical atom. So if you take stop, it is going to say yes and terminate the program. So you can have a loop that repeats many times and stops when you say stop. So how to do that? First, write this prompt. Enter an integer or stop to end the program. Then you read this integer and then ask, is this value equal to stop? If this value is equal to stop, then cut the program and terminate, because you have that this is the end of this line. After that, you have semicolon, which means you have another statement, and then you are going to try to go back over cut. This is not possible, and the only that remains to PROLOG is to terminate the program. So it's going to terminate the program, and if it is not stopped, then you go to the next line, because between this parenthesis and this parenthesis, we have practically if then else statement. So if this is satisfied, perform this operation. Else, perform y is x times x, compute the square, and then write square of this x is y, and you get the result. And then after you do that, then tell search engine is trying to go down to the end of this program, but you say, no, you just failed. You have to go back. And then it's backtracking to this, right? There is nothing here to create new result, nothing to create new result here, nothing here, nothing here, nothing here, nothing here, and repeat, yes, it succeeds. So now, after you hit this, it is going down. So it is going up, down, up, down, up, down, and terminating here in the middle. Now, this pair of parentheses and this semicolon are equivalent to an if-then-else statement. So if you have parentheses and condition, this condition can be satisfied or not satisfied. And then you have, after that, then part. So if this is satisfied, the PROLOG inference engine will go to then part and will perform whatever is there. It can be a big program or it can be a single line, whatever you want, but it is going to do this then part. If condition fails, you cannot continue. You don't go to a then part. You are dropping to the next line. And next line is this else part, because you have here semicolon. This is like having else part as a single, as a next statement that you have after this first line. So practically, it works same as if then else. And it has here pair of parentheses to make sure that this is visible to user, and it is a set of two things that will be used as a single construct. So if condition succeeds, perform then part. If it does not succeed, you cannot continue here. You drop to the next line, which is this else part. So if the condition fails, perform else part. If condition succeeds, perform then part. Now, let us use this to check whether something is a list. So our test program, whether L is a list, will write the list. And then we'll use the library function isList. Now, the library function isList of L is telling you whether this object L is a list or not. It can be whatever you want. If it is a list, then you are going to get that this is true. If it is true and satisfied, then you go here and write the word is. If you fail with this is list, then you write is not. So practically, I am displaying the list and then saying list is or is not, and then after that say a list. Okay, and put new line after that. So this little program is telling me whether something is a list or not. So I say, tell me whether 1, 2, 3 is the list. And then this program replies, 1, 2, 3 is a list. And if you ask whether 1, 2 is a list, this is not the list. This is a pair of two elements. So a binary tree that has here 1 and has here 2. Okay, so it is the 3 that has here 1 and here 2. So there is no empty list that terminates that, and therefore this is list is returning false. So you cannot satisfy this condition, and therefore you go to this is not. So the answer will be 1, 2 is not a list. Okay? And then the end of that is returned as true, which is not important, but you have that you get is a list or is not a list. Now, this can be used, therefore, in this case, where we have to check with if then else and this semicolon here, whether X is matching stop or not matching stop. You see that this here is symbolic constant, and this here is a variable, and this is pattern matching. So if these two patterns match, okay, if terminate the program. If they don't match, then go and continue. The same thing can be done in much more elegant way by using recursive calls. So you are not having this process which is done with, sorry, this one here, which is done with this pair of parentheses, but we are having recursive calls. So we are going to have this loop recursive that is going to ask the user, do you want to stop or you want to process this X? So we say enter an integer or stop to end the program. So the user can do two things, either to enter stop or not to enter stop. So we are going to read the value X after that, and then we'll call program called process X. So after that, we call process X. Where is process X? Well, this is this next line here. And this process has two different possibilities. This is if, then else. So we have two different things that we can do. The first one is to process stop. To process the value stop, this is going to be processed if we execute a cut. And after that, we have end of program. So PROLOG will say, aha, you have here stop. Let me go to see what happens here. And it is going to go over cut and will come with the search process between cut and dot here in between. And when it comes there, it knows that there is no way to go further and there is no way to go back. So it is going to say, yes, this succeeds. We terminate the program, have nothing to return because this is just input value stop. So nothing is returned and cannot go back, and therefore it terminates the program. If this is not performed, then you fail to stop the program and you drop down, and then you process value n. So you know that you have a number. Compute y is n times n and write the message square of n is n squared. Yes, sir. Question? No question. Okay. So after that comes new line. And then after new line, you call again loop recursive, this first one. So practically many of programs, like for example, the binary search program is practically searching something and then calling the same program to search from another position to another position. So it is recursively repeating that, but from two different places. So here, the loop recursive is calling process, and process is calling loop recursive. Recursion can have multiple stages. Program A is calling program B. Program B is calling program C. Program C is calling program A again. Or you can have A, B, C, D, and D is calling A. So you go through this. This is again recursive because you are in a loop that is having multiple function calls. So this has two of them. Loop recursive is calling process, and process is calling loop recursive. And this makes one nice loop that works same as this case before. Now, one thing that you can do is to test and debug your program by using this fail. Because if you have a program, you can simply say fail, and then the program will have to repeat. So here is an example how this works. So imagine that you have program append, and you want to see how this append works, and you have to test that. And to test the work of append, you are going to have two things. The first is to perform this append. So what I want to do is this. I have this append function that is appending x and y and giving 1, 2, 3. So what is this? This is the test of flexibility. And you want to say, I want to append two lists, list x and list y, to get list 1, 2, 3. Tell me what is x, what is y. Of course, it is going to give you, for example, 1 and 2, 3. Nice. But there are multiple solutions. So you want to see all of them. How to do that? Well, you write this test append that is appending x and y and giving 1, 2, 3. So what's going to happen here? This program will return x and will return y. But this is inside this rule here. So it is not going to display for you x and y. It is just going to compute them and give that to the next lines of code. So you say, okay, you gave me x and y. I'm going to display x, put a little bit of space, display y, and put new line. And then I have this x and y. After that, Prolog will drop down, and you say, you just failed. Ricardo, what is the question?
I understand how most of the Prolog programs work, and I can follow them, but what I cannot keep in my head is how do I tell which variables are the ones being returned for sure?
Well, you are always returning whatever is variable. In this case, returns x and y. Is that the question?
So it's always going to return those two regardless. Like it's going to be some permutation of both.
Yes, yes, yes. It is going to tell you you have empty list and 1, 2, 3 that you can append. You can append 1 and 2, 3, 1, 2, and 3, and 1, 2, 3, and empty list. It is giving you these results. So what you have here is that first time when you execute this, it is going to give you the first result, empty and 1, 2, 3. This is the first thing that is created here. Now, pay attention that when you give apps empty and 1, 2, 3, you put pointers inside where you are inside append. That is not visible to you, but is the place that was attained in having results of append. Then you display X and Y, and then you say you just failed. So search engine, after failing, is going backtracking, coming to this right. Right is a passive statement that is simply displaying the value. So you're not going to repeat that. It's coming here and finds append. Okay, say now continue from the place that you where you put your pointers to. So the append, sorry, put pointers after this solution, empty and 1, 2, 3. And then when you say continue, it is creating the new result, 1 and 2, 3. When you append 1 and 2, 3, you get 1, 2, 3. Okay, so it is creating this 2 pair. You display this pair and say you just failed. Again, backtrack, and you go back to append, execute append, backtrack, go to append. So each time when append creates the results, it is going to display results and fail. Well, after you exhaust all these XY combinations, what is going to happen then? Well, then append is not going to work. It is going to fail and will go out of this program because you continue after this comma here, if and only if you can create the new result. So after you exhaust all results, there is nothing more except to say no. There are no more solutions, and that's it. That's what you get. So this is test append that is used for debugging, for executing this multiple times. So it is a rule that says execute this, print results, and repeat over and over again as long as you have results. So you can put here any of your programs and see all the results that this program will generate. Is this somehow answer to your question or not?
Yeah, makes
Any other question? Okay. Okay. So we have this test and debug. So fail and repeat are purely procedural component in an unprocedural language. So you have to have something to control how the search engine is going and in what direction. So if you want to have control of that, you have fail and repeat that you can use for that. Here is an example how to test our programs for permutation. You know that we did delete. So delete was the first program that we developed, and then insert is opposite delete, and then permutation says take head and insert head in permuted tail. So you want to test whether our program permute works or not. So what I want to do, I want to put permute here to be tested and say permute 1, 2, 3 and give me permuted list. After that, I'm going to display this list. Pay attention that right is displaying lists. You don't have to say display component by component, display the whole list and put new line. And then after that, this is test permute, tell fail to search engine. So search engine say, oops, I just failed. I have to go back, hit permute, create new result, and then write this result, and then go to satisfy this. You just failed. Go back. And when you exhaust all this, you come here and say there are no other possibilities. Then you exit test permute because there is nothing that can be done. So here we go. Test permute. You get 1, 2, 3, 2, 1, 3, 3, 2, 1. And after that, no, there are no more combinations that I can make. So you are testing whether this program works fine. You can always make this 3 lines of code, execute the program, write the results, and fail. And this is good for testing these results. Now, if then else is something that is frequently used in finding maximum and minimum. Of course, you have maximum and minimum as library functions, but they work with 2 variables. So here is homemade maximum and minimum, and I have several slides that are investigating that. Not very exciting, I must say, but here we go. We have max1, which has x and y, and this maximum of x and y will be y if y is greater than or equal to x. And then you cut this program. So when you create these results, there is nothing more that can be done, and you go out. Here, if this is not the case, therefore, if x is not less than or equal to y, then you say maximum between x and y is x if x is greater than y. So you can say, why to repeat this here? Why to repeat this? And you can do that also without this cut. So what is the difference between max1 and this max without cut? And max3, which is based on if then else. So this max3 is telling you the following. If x is less than y, then return this m. I have here m, which is equal to y, this greater value, and then terminate the program. So this is if then else. We have here this pair of parentheses that can be omitted, by the way, and you have here semicolon, and then after that you have m is x. So you don't need to have this parenthesis, but it's good to have them just to see that this is first part and this is second part. So what I do here in max3, I am practically trying to find whether x is less than y. If this is not the case, I know that x is the maximum. So I immediately return m is x. And this is going to work perfectly same in this 4 that has no cut here. So here is the story. Max1, give me maximum between 1 and 7. M is 7. M is 7, M is 7, M is 7. All of them work the same way. However, if you want to do that flexibly, you can say, I have maximum between 1 and x. That gives the result 7. What is x? X is 7. It is here. And max2 is also giving you x is 7. Max3 is not able to do that. It is saying arguments are not sufficiently instantiated. Now, the idea is simply here that you have that this is an independent statement, this is another independent statement, and you are checking whether x is greater than y, regardless that you already know that. Here, you are not doing that. You are simply returning this is. And this is of course, not a flexible statement. It is not pattern matching statement. It is the assignment. And therefore, in this case, you have that x and y are inputs, m is output. And therefore, it is not to work flexibly like in this case. And this shows a little bit of flexibility. The flexibility is not complete, because if you put here, give me x and 7 so that the maximum is 7, you cannot find that, of course, because this can be any kind of value, and this is not working for obvious reasons. Now, the role of cut is here to eliminate multiple solutions also. So if I have that x, y gives me this minimum value, if x is less than y, I'm going to return minimum is x. And then I cut the program. In all other cases, I put minimum is y. Now, if I don't have this cut, then I will be able to proceed this from this point on, and will find maybe multiple results, which I don't want to do. Because if you want to find the maximum of a list or minimum of a list, which is a very frequent problem that we have frequently in Prolog. So we have minimum of the list that has a single component is X. That's fine. If there are more than one component inside, then there is a list that has head and tail. If the list has head and tail, then the minimum of that is obtained by finding minimum of tail. Take the tail, find the minimum of tail, and this is tail minimum. And then compute this minimum between head and tail minimum. And this is min that you return as the result. So how to find the minimum of the list? Minimum of the list is the smallest between head and minimum of tail. And that's fine, recursive, tail recursive reasoning. So you have to compute minimum of the tail, and then to compare minimum of the tail with the minimum, with the head to get the minimum value. However, what happens if you have, if we remove cut here, what happens then? Then minimum list will generate multiple minimum values or wrong results. For example, if you say, give me minimum of the list 4, 3, 2, 1, 2, 3, 1, it is going to give you 1. That's fine. But you can say, you know what, I want more. And then it is going to backtrack and go to try to find another minimum, which is 1 again. But if you continue like this, can create wrong results. If you have cut here, you are not going to get that. You are going to compute minimum and go out, and that's it. So you go here and return either minimum is X or minimum is Y. And there is nothing you can do after, because this minimum is X is cut, and this here is the last statement, so you cannot go back when you finish this first one. So min of this kind is going to be executed only once. And this is exactly what you want. So when you find the minimum, it's done. That's the minimum. There are no other minimums. Okay. You can have, of course, other program that is telling you how many times this one occurs in this list. That's another story. But if you have just this minimum, that's what you have to do. Now I have here a gazillion of examples with various minimums that have cut or have no cut, etc. We'll skip this. And this one here also. It is always working correctly. So all of them will give you minimum of maximum. For example, in this list, 1, 2, 3, 2, 1, you have that the maximum is 3, 3, 3, 3, 3. But if you want to do something flexibly, then some of them will work, some of them will not. Whenever you have that they have cut inside, they are not have flexibility because the cut is not permitting things to repeat twice. So it is either this or that. Minimum is X or minimum is Y, and that's it. And you don't have anything else that can happen. Now, if you want to have one program that is similar to those programs that come on the exam. So this was many times on exam. It says, write a program that is computing the sum of minimum and maximum of a list. So you have this list here, and you want to find the minimum. The minimum is 1. There are multiple ones, but you have to find minimum, which is 1. Okay, now, what happens with maximum? Maximum, if you see here, is 5. So when you find minimum 1, maximum 5, then minimum plus maximum, this ab is 1. And that is a typical problem of this kind. And so how to find list minimum? Well, you can say if the list has a single element, so you can use any kind of these programs, but you can write a different one. So you can say list minimum in this form as this program, or you can do it without minimum in this way. You say, if I have a single element, this is the minimum of the list. If I have more than one element, then I have first and second. If first is greater than second, then minimum is somewhere between this S and tail. So this is a big value. It is not the minimum. It is greater than S. So nobody knows where is S, somewhere inside. So if it is greater than S, compute minimum between S and T and return that value. And after that, cut the program. That's the end. Okay. If this is not the case, then you have that the list minimum will be between F and T, because this S is the smallest value. So if you have, if it is a smaller value, so S is going to be removed, and you will make the list with this head F and tail T. So this is the list with F and T, and file minimum from there. So by going this way, you are going to compute the minimum value without using the library function minimum, because you are going to call list minimum multiple times. Now, the question is, what is faster, this or the previous one? That's a different problem. However, this finds the minimum in these two lines. To find the maximum, we do exactly the same thing. So we are either finding maximum between FT or ST. Both FT and ST are reduced size. Sooner or later, you come to size 1, and list maximum of a single component is this F. So these are two beautiful little programs that find minimum and maximum, and then min plus max is for this list minimum plus maximum. List minimum is minimum of list. List maximum is maximum of list. And then we have that min plus max is computed as the sum of these two values. So that is what we have as the solution to this little program. And this kind of problems you're going to have on exam, something similar or of this nature. Now, I have here another example, which is numerical example of solving a numerical problem. And this can be done in PROLOG as well. So let me explain what problem is this. We want to find the root of this equation here. So find value x that is solution of f of x equals 0. So you have a polynomial, you can find the root of polynomial or something like that. So how to do that? Well, there are a variety of methods, gradient methods and whatever else, plenty of them in numerical analysis. One of them is called bisection method. So if you have that the function has 0 here, it can be, for example, an increasing function or a decreasing function, whatever you have. Let us suppose that it is an increasing function. So if I can find value A that is left from this solution and B that is right from this solution, so one has negative sign and the other has a positive sign, then I know that the solution is between them, between A and B. I don't know where is it, but I know that it is here. So by finding it, what we have to do? We have to find the middle value. So take A plus B divided by 2 and have this middle value. And then check whether this sign of function in middle value is same as sign in B. If it is, then move this B to middle value. And you get A, B that are closer than they used to be before. Then do the same thing. Find a plus b divided by 2. And you get this value here. And then ask whether the sign in this point is same as sign with b or same with a. It is same with a. These are negative, negative. This here was positive, positive. Therefore, move a to this middle point. And now you start from a, b here, and you have a, b that are much closer now. Obviously, if you repeat this several times, A and B are going to come closer, closer, and eventually will come so close that you are going to have the result. So how to solve this using C++? Of course, very simple. You have these 3 lines and then return 0 recursive. That means call itself, and you will get it in this way. In Prolog, it is not more complex than this. However, you can check whether you have correct values. Now, in this here program, let us say, I'm cheating a little bit because I don't have tests whether A is less than B. Because somebody can say, okay, I'll give you here that A is greater than B. What are you going to do then? Well, you have to check that. You can also have that A and B are on the same side of the solution. So you can have A here and B here. There is no solution in between. So that would be wrong also. So in my Prolog version of this program, I have all these tests. The first thing is to compute the function. How to compute function in Prolog? Well, you can say function of x is y if y is some expression here. For example, x times 1 minus x. So you see here that the solution is either 0 or 1. This is parabola. So it is going from 0 and going upside down, having 0 in x is 0 and x is 1. So we want to have this as a test program. And then program that is going to find this 0 is called 0. Okay. So the 0 of A, B, an anonymous variable, is going to be error message is A is greater than B. Is A is greater than B, say error A is greater than B, new line, and go out. Then if you have A and B that are on the same side of solution, they can be both or both negative. So what I'm going to do, I'm going to take the value of function in point A, value of function in point B. And I'm going to check whether A times B is greater than 0. So if it is plus plus or minus minus, this is going to satisfy this condition. And I say error product is greater than 0. So both of them are either positive, both of them are negative, and go out, and there is no solution. The third possibility is that A and B are right, that solution is right in the middle, so that you have that this x is computed as middle point is A plus B divided by 2, and then you have that you will return the value y if y is equal to 0. So you compute f of middle point is y, and then check whether y is arithmetically equals to 0. This happens once in 100 years that you hit exactly the middle point, but it can happen, and you say, okay, here is declare victory, x is middle point, return this x, and write exact result and go out. So these are all exceptional cases. What normally happens is that you are going closer, 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 and when you come to b minus a is some small value, you simply return x is a plus b divided by 2 and terminate the program. So this is the case where a and b are very close to each other. If they are not very close to each other, then compute middle value, which is a plus b divided by 2, compute function in that middle value, and compute function in point A. And then say, if you are on the same side, the product will be positive. And it is positive compute 0 between this mid value and B. And then you call this 0 again from the very beginning. So from here, you jump here, go through all this, and keep repeating. Otherwise, from A to middle. So either between middle and B, or from A to this middle value. And this gives you nice results. For example, if you say, I want the result between 1 and 2, you're going to get 1. If you want between -10 and 0, you get 0, numerically 10 to -8, and so on and so forth. Between 0.1 and 100, result is 1. So all of them work. But if you say, give me between 5 and 10, then you have error message. So this is the result of the bisection method. Now, we have this graph analysis here, which is something that we used in this test exam. And one thing that is important to notice here is that you can have the problem of this kind to find the shortest path between point A and point F. So how to do that? Well, you have here that distances or prices to fly between point A and point B are defined here. For example, this is $300 to go from A to B. Okay, so that is this value. And then from B to C, 1, and from C to F, 3. So the question is, flying from San Francisco to New York City, how to do that in the cheapest possible way? And this is what Orbitz and Travelocity and all of these companies are doing when you ask them, I want to travel from San Francisco to New York City. So they have here the situation go from A to B, 3 plus B to C, 3 plus 1 is 4, and 4 plus 3 is 7. So you can go A, B, C, F for cost that is 7. You can go 2 plus 3, 5 plus 1, 6. So this is cheaper. 2, 3, 1. I guess that you see what is the optimum solution. You can have here 2 plus 1, 3 plus 1, 4 plus 1, 5. Okay, so we have to find this optimum path from here to here. So how to find this path? If you look at this in a recursive way of thinking, you can say to come from the point A to point F, I'm going first to go to adjacent point. So a point that has direct link from A to D, there is link. So I'm going to fly from A to D, and then we'll say, now solve me the same problem between D and F. And that's all what you have to say. So to solve this problem, you're going to have link between two adjacent points, and then to solve the same problem from here to here. Now, the graph has these values 3, 1, 3, etc. So these are facts. So you have these facts here. Link between A and B is 3. Link between A and D is 2. So this is 3, this is 2. And then you have link between B and C is 1. And you have all these links. These are facts. And this defines the graph. Now, you say to fly between X and Y, this is going to cost me LXY. If there is a direct link between X and Y. So I go directly through this direct flight, pay LXY, and that's the solution of the problem. If there is no direct link between two adjacent points, so for example, if I go from D to C, there is a direct link. From D to E, there is a direct link. There is no link between D and B, for example, but between D and C and D and E, there is. Now, if there is no direct link, then I'm going to first go from X to an auxiliary adjacent position. So you go from X to adjacent position. This takes the length of travel or price LXA. And then I'm going to have path between this value A that I reached to the destination of the travel, which is this Y. I go from X to Y by going first from X to A and then from A to Y. And from X to A has this LXA, and from A to Y, which is path. So path is defined as a link plus another path. And then when I have that this is having the length LXA and this LAY, then the total length is going to be from X to Y, is going to be to go from X to Y, we go from X to A and from A to Y. Okay. You can also ask that you have only one stop or only two stops or whatever. That's what you do when you buy this in airline company, but this is going to generate all results. So if you want to go from A to F, in our case, from A to F, PROLOG will tell you that you have length 7, then I say, give me more, 6, 8, 6, 5, 6. So the best is 5. And the 5 is 2, 3, 4, 5. This is the shortest path. So it show me this. So you can have also put that in the list. You can say, okay, let us put these paths, whatever we have, let us find all of them. So find all lengths LXY in this path from X to Y, put that in LXY, take this LXY from this path program and put that in a list. Okay. And then you have that, return me this list. So between point X and Y, there is a list of different paths, different lengths, and put them all in this list. So I say path list between A and E is L, or A and F is L, and then you get these all solutions, 7, 6, 8, 6, 5, 6. The next normal thing would be, tell me what is the shortest path? What is the cheapest way to fly between these 2 points? And then we have these 5. So how to solve that problem? You can compute the minimum, same as before. So you can minimum of a list that has one element is X, minimum of list that has multiple elements is minimum of this tail, and then if tail is less than, if the result is less than head, then return this result M. In all other cases, return H. So this is the third of multiple minimum list and maximum list programs. Try to learn some of them. This is useful. So I have here the message. So compute path list and compute minimum and compute length, and then give the results. Number of different paths from X to Y is, and then writes all of them. And then minimum length is this X. Okay, so number of different paths from to F is 6. Minimum length from A to F is 5. And if you look at the whole program, you have here facts. So facts are definition of the graph. Then you have rules that are this here. And then you want to find all solutions. So find all paths and tell what is the cheapest flight by putting all of them in the list, and then find the minimum value from that list, and then have the message. So facts and rules are here, and this solves this problem in this elegant and short way. You also have such solution for your, in one of your homework assignments, we have that. maybe I can skip that. I can also say few words about this family relationship that was is male is female as his parent, and we have that you have a mother and child and father defined as female and parent, and then sibling one are people who have only one parent in common. For example, you have that X and Y are sibling one if they have the same mother. So mother is the same, and father X and father Y are different. Okay, so these are siblings one, and then you can have other sibling two are mother and mother are the same, father and father are the same, and these two people are different. Okay, and then you can have also brother two and sister two is sibling which is male, and sibling that is female, that's sister. And then you can have the case of either one or two parents in common. You can say sibling is somebody who has one parent in common. I don't care which one. And then these are siblings. You can have different cultural definitions, whatever you want. So you can have also definition of cousin, uncle, aunt, etc. So these are all things that I suppose you are familiar with, and I'm not going to spend more time on this. So what I would like at the end is to give you a little bit of overview of PROLOG language. So you have here a couple of programs that are not very important. One is with this musician, the other is the Towers of Hanoi, which I suppose you played with in this test exam, and then knapsack problem, which is a rather complex one. And now let us see what does exist in PROLOG. So in PROLOG, to summarize everything in 5 minutes, we have the possibility to read a file name. This is going to read a file name from the working directory. It is going to compile it. And if there are errors during this analysis, they are going to be reported, okay? In some of my version, this latest version reports that in red. Previously, it was in black. So depends whether you have a newest version or not. But consult is going to tell you do you have errors. So the cheapest way to do that is to put file name inside brackets. So what I usually do, I simply put on two screen Notepad++, and on the other I put a PROLOG execution. So you have Notepad++ that you can manipulate statements, change program, etc. And one of these, and then I go to window where you have PROLOG is running, and then take modified program and execute it. You can say make, which is reload all module files. I make listing of everything or listing of specific predicate and halt. All these things are what we have when we have the basic program manipulation programs. Then we have constants that are symbolic or integer or real or string. We have input out for read, write, and spaces and new line. And then relations and equalities. This is important. You have pattern matching. This is the most important of everything. So X is a pattern that matches pattern Y or not matches pattern Y. So these are two patterns that are matches. As opposed to that, you can have literal identity. So point literal, pointer identity where this is the same object and you have two different pointers to the same object. And then you have arithmetic case equality between two expressions. So evaluates expression 1, expression 2, and these expressions have to be instantiated before you can perform this. And then there is assignment. Expression 1 is X. Facts and rules. You have predicate and A, B, C. This is relation between A, B, and C. Likes somebody wine and food. Okay, so you have rule here that rules are made by, for example, in this example, having length of empty list is 0, length of non-empty list is the length of tail plus 1. And if you have a rule, you can have opposite of that by using not. Then you have list operations. List operation is list and length are frequently used. Member of the list, append, delete, select, and select. So delete is deleting, as you see here, all instances of elements. So if you have this list and what to eliminate this E, you get a list without that. Or you can remove only one instance, and this is done by using select. You can have also addressing directly components of the list. This is not particularly frequently used simply because this is just procedural access of an array. We don't do that. We do processing of array by using simply the tail recursion. You can get the last element in the list in this way, permutation, you can flatten. There is sum of list. If you want to compute the sum of list of random numbers, here is some list. You can create numerical list yourself. You can reverse list, same what you did in palindrome. You can sort list or msort or merge two lists. These are list operations. There are set operations, checking whether something is a set. That means it has all different elements. Union, intersection, and subtraction. You can create a subset of the set and merge two sets. Obviously, this eliminates all duplicates. So you can say merge two sets, and then when you merge them, all duplicates are going to disappear. And then find all set of and for all, we use them. You have also cut mechanism, fail and repeat that we studied today. Library functions, for example, random is creating random number. So random of 100 will give you one number between 0 and 99. This is random number. Sine, cosine, these are all classical function. Pi and e, look at them. You have reserved names for pi and e. These two constants are available. You don't have to do that. You can recognize whether something is integer, float, atom, variable. So this is for the analysis of program. You can have comments and assert for database operation. The bottom line is that PROLOG is a small language. You see that fits on these few slides, and that's all what you have. So that's the whole PROLOG. It is easy to learn all of them, but it is not that easy to solve problems using this because you have to have tail recursive thinking to solve the problems. And of course, PROLOG gives you powerful method of searching combinations, and by using pattern matching offers flexibility. That means that you have flexible results. Now, on Wednesday, we have midterm. Midterm is going to be 60 minutes, and we'll have 4 problems. All problems will be problem solving. Therefore, try to learn all this that exists in PROLOG. And what is legal is to use all slides that you have in the reader, and this material that is posted on iLearn that you also studied. However, nothing else. So please, no cut and paste from anywhere. Don't go to internet at all. Stay inside this material that is given to you in this class. We had in previous exam 25 copy-paste situations. All of them were given 0. If this repeats again to anybody, according to rules of CS department, I have to give you F in this class, and you have to repeat the class. Please, 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 don't do that. Don't touch anything outside material that was distributed here.